Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this big circle, and in the second question, we'll find out the area of this rectangle ABCD using two different methods. So we'll start with the first question. In the drawing, we have those two circles that touch each other at this point, point C. In addition, we know that this is line segment AC, that is equal to 6 units in its length. This is line segment CB, that is equal to 9 units in its length. This is tangent DE, that is tangent to this small circle at this point, point B. In addition, tangent DE is tangent to this big circle at this point. We define the point of tendency of tangent DE with this circle, this point as point M. In the next step, we'll focus on this point, point B. Point B is considered as an external point in relation to this big circle. So from this common external point, point B, we have tangent BM that is tangent to this big circle at point M. In addition, from the same common external point, point B, if we draw this straight line, it will cut the big circle at 2 points, point C and point A. In this way, we create a chord AC. Therefore, we can implement here rule 10. So repeat quickly on rule 10. Rule 10 is true in any circle, so in any circle, if AB is any chord in a circle and PT is a tangent to this circle at point T, then in this drawing, the following equation is true. That PT square equals to PA times PB. Again, PT square equals to PA times PB. So whenever, from a common standpoint of a circle, that is to say from point P, if you draw tangent PT, and from the same common standpoint, point P, you draw a straight line that cuts the circle at 2 points, point A and B. In this way, you will create chord AB. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can actually implement rule 10 in our drawing. In our drawing, we have the common standpoint, point B. From this common standpoint, point B, we have tangent BM, and from the same common standpoint, point B, we have here chord AC. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true, that BM square equals to BC times BA. Again, BM square equals to BC times BA. So I write it down. So according to rule 10, in this moment the following equation is true, that BM square equals to BC times BA. Repeat again. If we focus on the common standpoint, point B, then according to rule 10, the following equation is true, that BM square equals to BC times BA. BM is the missing tangent, so we leave it as it is, so BM square equals to BC. BC is 9 times BA. In total, BA equals to 9 plus 16, that is 25. So I can find out that according to rule 10, BM square equals to 9 times 25. here we take a root out of this equation and we get that BM equals to the square root of 9 is 3 times the square root of 25 is 5. So in total BM equals to 3 times 5, that is 15. So the length of tendon BM is 15 units. This is tendon BM that is equal to 15 units in its length. In the next step, we will do a construction. That is to say, from point C, that is the point of tendency of those two circles, we will draw a straight line towards DE. From point C, we draw a straight line towards DE. And we define the touching point of the common tangent, this common tangent with DE, this point is point M. Actually, CN is a common tangent that belongs to both circles. CN is a tangent to this small circle at point C, and Cn is also tangent to this big circle at the same point, point C. So Cn is a common tangent that belongs to both circles. In the next step, we join point C and M together by a straight line. In the next step, we'll focus on this common extra point, point N. From this common extra point, point N, we have two tangents to the small circle, tangent NC and tangent NB. And according to rule 2, they are equal to each other. That is to say, NC equals to NB. I repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common extra point to a circle are equal. In the drawing, we have a circle. This is the common extra point, point P. From this common extra point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So what I mentioned before, we can implement rule 2 in our drawing. In our drawing, from this common extra point, point N, we have two tangents to this circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. That is to say, NB equals to NC. In the next step, I will copy triangle CNB in a new page, and we will analyze this triangle, triangle CNB. Actually, this is triangle CNB that I copied from the original drawing. It is triangle CNB, side CN equals to side NB. Again, this right triangle CNB, side CN equals to side NB according to rule 2. And we have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of this side CN we have this angle, angle CBN, and in front of this side NB we have this angle, this is actually angle NCB. And according to the rule that I mentioned, because of the fact that those two angles are located in front of those two equal sides, they must be equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be equal to alpha, because of the fact that those two angles are located in front of those two equal sides, and therefore they must be equal to each other in their sizes. So actually found out that angle NCB equals to alpha and angle NBC also equals to alpha. So actually this is angle NCB that is equal to alpha, and this is angle NBC that is also equals to alpha. We will continue to focus on this common side point, point N. From this common side point, point N, we have two tangents to the big circle, tangent NC and tangent NN. And according to rule 2, they are equal to each other. That is to say, NC equals to NM according to rule 2. In the next step, I'll copy triangle CMN in your page and we'll analyze this triangle, triangle CMN. So actually, this is triangle CMN that I copied from the original drawing. According to rule 2, side CN equals to side MN. Again, CN equals to MN according to rule 2. And according to the rule that I mentioned, the rule that says that in front of equal sides in the triangle, there are equal angles. So in front of this side CN, we have this angle that is actually angle CMN. And in front of this side MN, we have this angle that is actually angle NCM. And because of the fact that those two angles are located in front of those two equal sides, they must be equal to each other. So if the size of this angle is beta, then the size of this angle must be also equal to beta, again because of the fact that those two angles are located between those, because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other. Okay. So if we found out that this is angle MCN, this is equal to beta, and this is angle NMC, that is also equals to beta. So angle MCN, this angle equals to beta, and this is angle NMC, that is also equals to beta. In the next step, I'll copy the big triangle MCN. The big triangle MCN consists of those two triangles, triangle MCN and triangle NCB. So I'll copy the big triangle MCB in a new page, and we'll analyze this big triangle MCB. So actually, this is triangle MCB that I covered from the original drawing. We have the rule that states that the sum of the angles in any triangle is equal to 180 degrees. So the rule is true in any triangle, and therefore it is especially true in this triangle, triangle MCB. So actually the sum of the angles in triangle MCB is equal to 180 degrees. So which angles we have in this triangle MCB? We have this angle that is angle alpha, plus this angle that is beta, plus this angle that is beta plus alpha. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. So in this side of the equation we have alpha plus alpha, that is 2 alpha, beta plus beta is 2 beta, so in total we should found out that 2 alpha plus 2 beta equals to 180 degrees. Here we divide this equation by 2, and finally we get that alpha plus beta equals to 90 degrees. That is to say, this angle MCB is equal to alpha plus beta, it is equal to 90 degrees in its size. So angle MCB is equal to alpha plus beta is a right angle. So actually, this is angle MCB that is equal to 90 degrees in its side. Again, this is angle MCB that is a right angle. It is given us the question that AB is a straight line. And according to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So the sum of the angles on the left side of the straight line AB at point C must be equal to 180 degrees according to rule 3. So which angles we have at the left side of AB at point C? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we'll join points A and M together by a straight line. And we'll focus on the big circle. Actually, in the big circle, we have peripheral angle ACM. This is peripheral angle ACM, and the size of this peripheral angle ACM is equal to 90 degrees according to rule 3. Now we can implement here rule 5. So I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. In the drawing we have a circle, and this is peripheral angle MAN. And peripheral angle MAN is a right angle. And because of the fact that peripheral angle MAN is a right angle, peripheral angle MAN must subtend on the diameter of the circle. And peripheral angle MAN subtends on MN, and therefore MN must be the diameter of the circle according to this rule, rule 5. So any peripheral angle that is equal to 90 degrees in its size must rest on the diameter of the circle. We can definitely implement rule 5 in our drawing. Why? Because in our drawing, if we relate to the big circle, inside the big circle we have peripheral angle ACM. This is peripheral angle ACM, and peripheral angle ACM is equal to 90 degrees in its size, and according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. But peripheral angle ACM, that is a right angle, subtend on AM, and therefore AM must be the diameter of this circle according to rule 5. So I write it down. We found out that AM is the diameter of this circle. So repeat again, according to rule 5, chord AM is the diameter of the circle. Diameter of the big circle. We also know that the center of the circle must be located on the diameter of the circle. Again, the center of the circle must be located on the diameter of the circle. So here the center of the circle must be located on AM, that is the diameter of this circle. So this is the center of this circle. We define the center of this big circle as O. You can see here that point O is located on AM, that is the diameter of this big circle. So actually, point O is the center of this big circle, point M is a point on the big circle itself, therefore OM is the radius of this circle. We define the radius of this big circle as R, so OM equals to R, which is the radius of the big circle. And because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever your radius is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I'll copy the right big triangle A and B in a new page, and we'll implement the Pythagoras theorem on this right big triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a relation for Pythagoras theorem. The length of the hypotenuse AB of the right triangle A and B is 16 plus 9, that is 25. MB equals to 15 units in its length according to rule 10. And AM is the missing side. So actually, this is the right triangle A and B that are copied from the original drawing. According to the Pythagoras theorem, in this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. So I write it down. AB squared, that is the square of the hypotenuse, is equal to AM squared plus MB squared. The hypotenuse AB is 25, therefore AB squared is 25 squared, that is 625. and it is equal to AM square. AM is the missing side, so we leave it as it is. So it is AM square plus MB square. MB is 15, therefore MB square is 15 square, that is 225. So in total we can find out that 625 equals to AM square plus 225. Here we subtract 225 from this equation, and we get that 625 minus 225 is 400, so 400 equals to AM square. Here we took a root out of this equation, and finally we get that AM equals to the square root of 400, that is 20. So we found out that the length of the hypotenuse AM, the length of side AM is not the hypotenuse, the length of side AM is equal to 20 units. We already found out that AM, according to rule 5, AM is the diameter of the big circle. Again, AM is the diameter of the big circle. The radius of any circle, the radius R of this big circle, the radius R must be equal to the diameter AM over 2. The diameter AM equals to 20 units in its length, so 20 over 2 is the radius of this circle. The length of the radius, that is 10. 20 over 2 is 10, so the radius of the big circle equals to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle, is equal to pi times the radius of the circle squared. Repeat again. We know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is 10, and therefore the radius squared is 10 squared. So in total, we can find out that the area of the big circle equals to pi times 10 squared. So it is pi times 10 squared. 10 squared is 100. So in total, we can find out that the area of this big circle equals to either 100 pi square units, or in terms of numbers, the area of the big circle equals to 314.159 square units. And that is the answer to the question. Repeat again. We actually found out that the area of this big circle, it is equal to either 100 pi square units, or in terms of numbers, the area of this big circle is equal to 314.159 square units. So finish with the first question. In the next step, I will present for you the second question, and we will solve the second question by using two different methods. Our mission in this second question is to find out the area of this rectangle ABCD. So in the domain we have rectangle ABCD, and we have also this semicircle. We know that this is line segment AM, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So we'll start with the first method. First of all, we know that ABCD is a rectangle. So all those 4 angles inside rectangle ABCD are right angles. So actually this is a right angle. This is also a right angle. This is a right angle. And finally this is also a right angle. In the next step, we'll define the center of this semicircle. This point is point O. We'll also define the radius of this semicircle as x. So point O is the center of the semicircle. Point A is the point on the semicircle itself. Therefore, OY is the radius of this semicircle, that is equal to x units in its length according to our definition. In the next step, we will define the point of tendency of tangent DC with this semicircle. This point is point E. and we join points O and E together by a straight line. Point O is the center of the semicircle, point E is the point of the semicircle itself, therefore OE is the radius of this semicircle that is equal to x units in its length according to our definition. So OE equals to x. Because of the fact that the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle, whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. By doing this construction, we created here quadrilateral DEOA. Inside this quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OE, inside quadrilateral DEOA, we have 4 right angles, and according to rule 5, any quadrilateral that has four right angles must be this rectangle, not a square. So we relate to this quadrilateral DEOA is a rectangle because it has 4 right angles. So quadrilateral DEOA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DA. But EO is x, it is the radius of the circle that is x, therefore DA must be also equal to x units in its length. DA equals to x. Okay. In the next step, we join points O and M together by a straight line. What is the definition of line segment OM? Line segment OM starts from point O, that is the center of the semicircle, and then at point M, that is a point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OM is the radius of this semicircle that is equal to x units according to our definition. In the next step, we define the length of this line segment OB as A, and we define the length of this line segment MB as B. In the next step, I'll copy the right triangle OMB in a new page, and we'll implement the Pythagoras theorem on this right triangle OMB. Here by PT is the equation for Pythagoras theorem. So actually, this is the right triangle OMB that I copied from the original drawing. This right triangle OMB according to the Pythagoras theorem, MO squared, that is the square of the hypotenuse, equals to MB squared plus BO squared. So I write it down. MO squared, that is the square of the hypotenuse, is equal to MB squared plus BO squared. MO is x, therefore MO square is x squared. And it is equal to MB squared. MB is A, therefore MB squared is A squared plus BO squared. Plus MB squared. MB is B, therefore MB squared is B squared. So in total, we have found out that x squared, according to equation 1, x squared equals to A squared plus B squared. Okay? Here, OB is A, therefore B squared is A squared. And MB is B, therefore MB squared is B squared. So in total, according to equation 1, x squared equals to x squared equals to A squared plus B squared. This is according to equation 1. In the next step, I will copy the right triangle AMB in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle AMB. The hypotenuse AM equals to 5 units in its length, according to what is given as the question. Then and side AB of the right triangle AMB equals to x plus A, and MB, side MB equals to B units in itself, according to our definition. So I'll copy this right triangle AMB in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle AMB. Here by PT is the version for Pythagoras theorem. So really, this is the right triangle AMB, this is a copy from the original drawing. In this right triangle AMB, MA squared, that is the square of the hypotenuse, must be equal to MB squared plus BA squared. Again, AM squared equals to MB squared plus BA squared. So I'll write it down. MA squared, that is the square of the hypotenuse, is equal to MB squared plus AB squared. MA is 5, therefore MA squared is 5 squared, this is 25, and it is equal to MB squared. MB is B, therefore MB squared is B squared plus AB squared. AB is x plus A, therefore AB squared is x plus A squared. So in total we should find out that according to equation 2, 25 equals to B squared plus x plus A squared. X plus A squared equals to x squared plus A squared plus 2 times x times A. So in this side of this equation, equation 2, we have the expression of A squared plus B squared. But according to equation 1, we already found out that A squared plus B squared equals to x squared. Therefore, we can substitute A squared plus B squared in this equation 2 by x squared from this equation, equation 1. We'll do it now, and we get that according to equation 2, 25 equals to A squared plus B squared is x squared. We have again x squared plus x squared plus 2xa. So in total we should find out that according to equation 2, 25 equals to x squared plus x squared is 2x squared plus 2xa. So repeat again. Actually found out that according to equation 2, 25 equals to 2x squared plus 2xa. Here we'll divide this equation 2 by 2, and we get that 25 over 2 is 12.5, and it is equal to 2x squared over 2 is x squared, plus 2xa over 2 is xa. So in total we should find out that according to equation 2, 12.5 equals to x squared plus xa. Here we take out x as a common factor from those two expressions. So inside the brackets we left only with x plus a. So in total, according to equation 2, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. Repeat again, our mission is to find out the area of rectangle ABCD. Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. Therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB times the width. The width is DA. So in total, we found out that the area of rectangle ABCD equals to AB times DA. AB in total is x plus a. AB is x plus a. And DA is x. So in total, we found out that the area of rectangle ABCD equals to x plus a times x, or x times x plus a. But according to this equation 2, we have already found out that x plus a times x is 12.5. Therefore, we can substitute x plus a times x by 12.5. We do it now, we get that x plus a times x according to equation 2 is 12.5. So in total, we should find out that the area of rectangle ABCD equals to 12.5 square units. So we actually finished with the first method, and then again we actually found out that the area that we are looking for in this question, the area of this rectangle ABCD, equals to 12.5 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD in the second method. So first of all, you know that ABCD is a rectangle, therefore all those four angles inside rectangle ABCD are right angles. So actually, this is a right angle, this is also a right angle, this is a right angle, and finally this is also a right angle. In the next step, we define the center of this semicircle. This point is point O, and we define the radius of this semicircle as x. So point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to x units in itself according to our definition. In the first method, we have already found out that AD equals to x, so I will not repeat on the explanation. AD is x. According to the first method, 8 is x. In the next step, we will define the point of tendency of tangent DC with this semicircle. This point is point E. And we will join points O and E together by straight line. Okay, actually it is not necessary here. So in the next step we define this point as point N, and we join points M and N together by a straight line. By doing this construction, we can do peripheral angle NMA. This is peripheral angle NMA, and this peripheral angle MNA subtend on AN. But AN is the diameter of the semicircle. And according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So this peripheral angle NMA that subtend on AN, that is the diameter of this circle, must be equal to 90 degrees in its size. So I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees. We know that AB is the diameter. Again, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees. We know that AB is the diameter of this circle, and this is angle, peripheral angle ACB. Peripheral angle ACB definitely subtend on AB, which is the diameter of this circle, and therefore peripheral angle ACB must be equal to 90 degrees in its size according to this rule, rule 7. So actually we have already implemented rule 7 in our drawing. Because of the fact that this is peripheral angle AMAN that subtend on AN, that is the diameter of this semicircle, therefore peripheral angle MAN must be equal to 90 degrees in its size. So this is peripheral angle MAN, this is a right angle, according to rule 7. In the next step, we define this angle as alpha, and we will focus on the right triangle AMN. In this right triangle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, we focus on this right triangle A and B. The right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Again, why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. In the next step, I'll copy the right triangle AMN and this right triangle AMB in a new page, and we will prove that those two right triangles are similar to each other according to angle similarity rule. Side AB equals to, here we define this line segment OB is A, and therefore in total side AB equals to x plus A. Again, side AB in total equals to AO, that is x, plus OB, that is A. So in total side AB equals to x plus A. It is given as the question that AM equals to 5 units in its length. So actually, those are the two right triangles that are coming from the original drawing. This is triangle A and B, this is triangle A and N. In the next step, we'll prove that those two right triangles are similar to each other according to angle, similarity rule. So why those two right triangles are similar to each other? But before that, what is the length of line segment AN? We already found out that we know that AN is the diameter of the semicircle. If the radius of the semicircle equals to x, the diameter must be equal twice as big as the radius. So the diameter must be equal to 2x. So AN equals to 2x. It is the diameter of the semicircle that is equal to 2x units in its length. So AN equals to 2x. Again, AM equals to 5. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually, this is angle MBA in the right triangle AMB, and it is equal to this angle, that is actually angle AMN in the right triangle, triangle AMN. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is actually angle A, that is a common angle that belongs to both triangles. So you can write down that angle A equals to itself as a common angle that belongs to both triangles. You can see in the original drawing, this is angle A, that is a common angle that belongs to both triangles. You can see it easily that angle A equals to the right triangle AMB, and this angle A also belongs to the right triangle AMN. So angle A is a common angle that belongs to both triangles. So you can write down that angle A equals to itself as a common angle that belongs to both triangles. So if we relate to angle A as it belongs to this right triangle AMB, it will be defined as angle MAB. Angle A equals to itself. So if we relate to angle A as it belongs to the right triangle AMN, it will be defined as angle MAN. So this equation means that angle A equals to itself. We just call to angle A two different names. So angle A equals to itself as a common angle that belongs to both angles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So this is angle A and B in the right triangle, A and B, and it is equal to this angle, that is actually angle M and A in the right triangle, triangle AMN. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually found out that all the triangles in this right triangle A and B are correspondingly equal to all the triangles of this right triangle AMN, and therefore those two right triangles are similar to each other according to angle similarity rules. So I write it down. We actually found out that this right triangle A and B is similar. This is the sign of similar to the right triangle AMN according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side MA of this right triangle A and B over side AM of this right triangle AMN is equal to side AB of this right triangle AMB over side MA of this right triangle AMN. So I repeat again. We actually found out that side MA of the right triangle AMB over side NA of the right triangle AMN equals to side AB of the right triangle AMB over side AM of the right triangle AMN. AM is 5 according to what is given as the question. We already found out that AN is the diameter of the semicircle, that is 2x, and it is equal to AB. AB is x plus A. Over MA. MA is 5 according to what is given as the question. So in total, according to equation 1, we actually found out that 5 over 2x equals to x plus A over 5. Here we cross multiply this equation, equation 1. And finally we get that according to this equation, equation 1, five times 5 is 25, and it is equal to 2x times x plus A. So here we divide this equation 1 by 2, and we get that according to this equation 1, 25 over 2 is 12.5, and it is equal to 2x over 2 is x, so in total this expression equals to x times x plus A. So in total, according to equation 1, we actually found out that x times x plus A equals to 12.5. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of our rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB times the width. The width is DA. So in total we shall find out that the area of rectangle ABCD equals to the length AB times the width, that is DA. But AB equals to x plus A. AB is x plus A and DA is x. So in total we shall find out that the area of rectangle ABCD equals to x plus A times A. It is equals to x plus A times A. But according to equation 1, x plus A times x is 12.5. Therefore we can substitute x plus A times x by 12.5. According to equation 1. So x plus A times x is 12.5 according to equation 1. So in total we shall find out that the area of rectangle ABCD equals to 12.5 square units. So we actually found out that in both methods the area of this rectangle ABCD equals to 12.5 square units. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our mission in the first question is to find out the area of this big circle. So, in the drawing we have two circles that are tangent to each other at this point, point C. In addition, we know that this is line 7 CB, that is equal to 9 units in its length. This is line 7 AC, that is equal to 16 units in its length. This is tangent DE, that is tangent to this small circle at this point, point B. In addition, tangent DE is tangent to this circle at this point. We find the point of tendency of tangent DE with this circle as point M. So, in the next step, we focus on this common external point, point B. Point B is a common external point in relation to this big circle. For this common external point, point B, we have tangent BM, that is tangent to this big circle, point M. In addition, from the same common external point, point B, if we draw this straight line BC and extend it, it will cut the big circle at 2 points, C and A. In this way, we get chord CA. So actually, all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true: that BM square equals to BC times BA. Again, BM square equals to BC times BA. Okay, again, if we focus on the common external point, point B, according to rule 10, the following equation is true: that BM square equals to BC times BA. BM is the missing side, so we leave it as it is, and it is equal to BC. BC is 9. BC is 9 times BA. BA in total is 9 plus 16, that is 25. So BA is 25. So in total, we actually found out that according to rule 10, BM square equals to 9 times 25. Here we took a root out of this equation, and finally found out that BM equals to the square root of 9, that is 3, times square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. So we found out that the length of this tangent BM is 15 units. In the next step, we did the construction, that is to say, from this point of tendency between the two circles, we drew the common tangent that belongs to both circles. Again, point C is the point of tangency of the two circles. That is to say, they touch each other at this point, point C. So actually we did a construction by drawing a common tangent that belongs to both circles. And we define the touching point of the common tangent with tangent DE. This point is point N. Again, CN is the common tangent that belongs to both circles. CN is the tangent to this small circle, and CN is also tangent to this big circle. Therefore, CN is the common tangent that belongs to both circles. Okay, so in the next step, we focused on this common extreme point, point N. From this common extreme point, point N, we have two tangents to the small circle, tangent NC and tangent NB. And according to rule 2, they are equal to each other. That is to say, NC equals to NB. In the next step, I copied the triangle CNB in the new page and analyze this triangle, triangle CNB. So actually, this is triangle CNB that I copied from the original drawing. According to rule 2, CN equals to NB. And according to the rule that says that in front of equal sides in the triangle there are equal angles, we get that in front of this side CN we have this angle, in front of this side NB we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be equal to each other. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha according to the rule that I mentioned. So in total we should find out that this is angle NCB that is equal to alpha, this is angle CBN that is also equal to alpha. In the next step, we join point C and M together by a straight line. And we continue to focus on this common extreme point, point N. From this common extreme point, point N, we have two tangents to the big circle, tangent NC and tangent NM. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. In the next step, I copied triangle NCM in a new page and analyze this triangle, triangle NCM. So actually, this is triangle NCM that I copied from the original drawing. According to rule 2, CN equals to NM. And according to the rule that I mentioned, that in front of equal sides in the triangle there are equal angles, so in front of this side CN we have this angle, in front of this side MN we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must also equal to each other. So if the size of this angle is beta, then the size of this angle must be also equal to beta. So in total we should find out that this angle NCN equals to beta, and this angle NMB also equals to beta. In the next step, I copied the big triangle MCB in a new page and we analyze this triangle, triangle MCB. This is the triangle MCB that I copied from the original drawing. You have the rule that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and especially it is true in this triangle, triangle MCB. So what is the sum of the angles in this triangle MCB? We have this angle alpha plus this angle beta plus this angle that is beta plus alpha. In total, it must be equal to 180 degrees. Angle MCB equals to beta plus alpha. This is angle MCB that is in total equals to beta plus alpha. So in total, the sum of the angles in this triangle MCB equals to 180 degrees. So alpha plus beta plus alpha must be equal to 180 degrees. So in this end of the question we have alpha plus alpha is 2 alpha and beta plus beta is 2 beta. So in total we have 2 alpha plus 2 beta must be equal to 180 degrees. We divided this equation by 2 and finally found out that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So this is angle alpha plus beta or angle NCB that is equal to 90 degrees in its size. So actually this is angle MCB, this is angle MCB that is equal to 90 degrees in its size. AB is a straight line according to what is given as the question. So if we focus on the left side of the straight line AB at point C. Here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is a right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees. And therefore this missing angle must be equal to 90 degrees in its size. So in the next step, we join points A and M together by straight line, and we focus on this big circle. Inside this big circle, we have peripheral angle ACM. Peripheral angle ACM equals to 90 degrees in its size. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. And this is peripheral angle ACM, that is the right angle, and therefore according to rule 5, peripheral angle ACM must subtend on the diameter of the circle. But peripheral angle ACM subtend on AM, and therefore AM must be the diameter of the circle according to rule 5. Okay, again, according to rule 5, chord AM is the diameter of the big circle. Okay? So AM is the diameter of this big circle. And we know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. AM is the diameter of the big circle, and therefore the center of this big circle must be located on AM. So this is point O. It is located on AM, that is the diameter of the circle, and point O is the center of this circle. So point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this big circle. We define the radius of this big circle as R. So OM equals to R, and because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever your radius is drawn to the point of tendency, then tangent DE will be perpendicular to the radius OM. If D is perpendicular to OM, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I copied the right angle A and B in a new page and implemented the Pythagoras theorem in this right angle, triangle A and B. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right angle A and B that I copied from the original drawing. In this right angle A and B, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. Again, AB in total equals to 16 plus 9, this is 25, and MB equals to 15. AB is 25, therefore B squared is 25 squared, that is 625, and it is equals to AM squared. AM is the missing side, so we leave it as it is, so it is AM squared plus MB squared. MB squared is 15, the MB is 15, therefore MB squared is 15 squared, that is 225. So in total, according to the Pythagoras theorem, we actually found out that 625 equals to AM squared plus 225. Here we subtract 225 from this equation, and finally found out that 625 plus 225 is 400, so 400 equals to AM squared. Here we took out of this equation and finally found out that AM equals to the square root of 400, that is 20. AM equals to 20 units in its length. AM is the diameter of the semicircle, so we actually found out the diameter of this AM is the diameter of the big circle. Here AM is the diameter of the big circle. So the diameter AM of the big circle equals to 20 units, and therefore the radius must be equal to half of it. That is to say, the radius must be equal to 20 over 2, that is 10. The radius of this big circle must be equal to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of the big circle must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, and therefore the radius squared is 10 squared. So in total the area of the big circle must be equal to pi times 10 squared. So it is pi times 10 squared. 10 squared is 100, so in total the area of this big circle must be equal to either 100 pi square units, so in terms of numbers, the area of this big circle must be equal to 314.159 square units. We finished with the first question. In the next step, I presented to you the second question, and we solve the second question in two different methods. our mission in the second question is to find out the area of the rectangle ABCD. So in the drawing we have rectangle ABCD and we have this semicircle. We know that this is line segment AM, that is equal to 5 units in itself. Again, our mission is to find out the area of this rectangle ABCD. So we start with the first method. So in the first method, we know that ABCD is a rectangle, therefore all those 4 angles inside the rectangle ABCD are right angles. In the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. And we define the point of tendency DC with this semicircle as A. In the next step, we join points O and E together by that line. Point O is the center of the semicircle, point E is the point on the semicircle itself, therefore OE is the radius of this semicircle, that is equal to x units in itself according to our definition. Because of the fact that the radius OE is on to point E, that is the point of tendency of tangent DC with this semicircle, whenever you have a radius that is on to the point of tendency, then tangent DC will be perpendicular to the radius EO. If this is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing this construction, we can do the quadrilateral DEOA. Inside this quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, you get 200. Inside this quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to quadrilateral DEOA as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DA. But EO is x, therefore DA must be also equal to x units in its length. In the next step, we join points O and M together by side line. OM is the radius of the circle, of the semicircle, that is equal to x. We define this line segment OB as A and this line segment BM as B. In the next step, I copy this right angle MOB in the new page and we implemented the Pythagoras theorem on this right angle MOB. So actually this is the right angle MOB that I copied from the original drawing. According to the Pythagoras theorem, in this right angle MOB, x squared equals to a squared plus b squared. Again, x squared equals to a squared plus b squared. This is equation 1. In the next step, I copied the right triangle A and B in a new page and implemented the Pythagoras theorem on this right triangle A and B. This is the right triangle A and B that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle A and B, AM squared equals to MB squared plus AB squared. AM is 5, therefore AM squared is 5 squared, that is 25. And it is equal to MB squared. MB is B, therefore MB squared is B squared plus AB squared. AB is x plus A, therefore AB squared is x plus A squared. So in total, according to equation 2, I should found out that 25 equals to B squared plus x plus A squared. So 25 equals to B squared plus x plus A squared. X plus A squared equals to x squared plus A squared plus 2 times x times A. In this side of equation 2, we have B squared plus A squared. And according to equation 1, b squared plus a squared equals to x squared. So we can substitute b squared plus a squared in this equation 2 by x squared from equation 1. We did it, and we should have found out that 25 equals to b squared plus a squared is x squared. And we have x squared again plus 2xa. So in total, according to equation 2, 25 equals to x squared plus x squared, that is 2x squared plus 2xa. So according to equation 2, we should have found out that 25 equals to 2x squared plus 2xa. Here we divided the equation 2 by 2, and finally found out that 25 over 2 is 12.5. 2x squared over 2 is x squared, and 2xa over 2 is xa. So in total, we actually found out that 12.5 equals to x squared plus xa. So 12.5 equals to, here we took out x as a common factor from those two expressions, so inside the brackets we left only with x plus a. So in total, according to equation 2, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. Actually, the area of any rectangle equals to the length of the rectangle times the width. The length of this rectangle, and therefore the area of rectangle ABCD must be equal to the length of the rectangle, ABCD times the width. The length of this rectangle ABCD is AB, and the width is DA. So in total, the area of rectangle ABCD must be equal to AB times DA. AB in total is x plus a, and DA is x. So in total, again, AB is x plus a, and DA is x. So in total, the area of rectangle ABCD must be equal to x plus a times x. But according to equation 2, x plus a times x is 12.5. Therefore, we can substitute x plus a times x in this equation by 12.5. We did it, and we found out that in total, the area of rectangle ABCD equals to 12.5 square units. We finished with the first method. In the next step, I presented to you how to find out the area of this rectangle ABCD according to the second method. In the second method, here we know that ABCD is a rectangle, and therefore all those four angles are right angles. We define the center of this semicircle, this point as point O. We define the radius of this semicircle as x. So OA is the radius of the semicircle, that is x. We have already found out that DA equals to x in the first method. In the next step, we define this point as point N, and we join points N and M together by a straight line. We define this line's length OB as A. By joining points N and M, we can do peripheral angle NMA. This is peripheral angle NMA that subtends on AN, that is the diameter of the semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its side. And therefore, this peripheral angle NMA that is subtended on the diameter of the semicircle must be equal to 90 degrees in its side according to rule 7. So in the next step, we define this angle as alpha, and we focus on this right angle AMN. In this right angle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. In the next step, I copy the right triangle A and B and the right triangle A and N in the new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So those are the two right triangles that are going from the original drawing. This is the right triangle A and B, and this is the right triangle A and N. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. This is angle A, that is a common angle that belongs to both triangles, so we can find out that angle A equals to itself as a common angle that belongs to both triangles, and finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the triangles of this right triangle A and B are correspondingly equal to all the triangles of this right triangle A and N, and therefore those two right triangles are similar to each other according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that A over AN equals to AB over AM. MA is 5, AN is 2x, AB is x plus a, and AM is 5. So here we cross multiply this equation in equation 1, and finally found out that according to this equation in equation 1, 25 equals to 2x times x plus a. Here we divided this equation in equation 1 by 2, and finally found out that 12.5 equals to 2x over 2 is x, so in total 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. Actually, the area of any rectangle equals to the length of the rectangle times the width. Therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABC times the width. The length of this rectangle ABCD is AB, and the width is DA. Again, the length is AB and the width is DA. AB equals to X plus A and AD equals to D. AB is X plus A and AD is X. So in total, the area of rectangle ABCD equals to X plus A times X. But X plus A times X is 12.5 according to equation 1. Therefore, we can substitute X plus A times X by 12.5 according to equation 1. We did it, and actually in total found out that the area of this rectangle ABCD equals to 12.5 square units. So in both methods, we found out that that we are looking for in this question, the area of rectangle ABCD is equal to 12.5 square units. Okay, thank you very much.